We're talking about gravitational lensing, Einstein rings, and dark matter. And we're going to see how we determine the mass of something through gravitational lensing and other methods. Okay. So this is the summary of tonight's journey. Prepare yourself. So first, we're going to start with some foundations. So there were two views on gravity. The first original view was Newton's view. Well, actually, before that, preceding that, in the geocentric version of the universe, people thought that gravity was attracted towards the center of Earth. So all the heavenly bodies, all the planets would just get pulled towards the center of Earth because it was special. But Newton discovered that gravity is an instantaneous force between masses, F equals gmm over r squared, and light was thought to have no mass. So gravity doesn't act on light. Now, Einstein revised this and defined gravity as the curvature of space-time caused by mass energy. And light follows the geodesic, which is the shortest line, and the straightest path in curved space-time. So massive objects like black holes can curve space-time, and they bend the photons. Okay, so this is the representation of Einstein's field equations as tensors. We're not going to go too much into tensors, but I will describe them a little bit. And this is what the geometry around Earth would look like. This is how gravity would bend with Earth. It's like a gravity well. So this is like the most math you're ever going to see. Don't worry, this is it. I promise. So we're just going to break down the equation a little bit. So
could you speak a little slower?
Of course. So G mu nu is Einstein tensor and it encodes the space-time curvature. Lambda G mu nu is the cosmological constant term, which drives the accelerating expansion of the universe. Einstein originally thought this lambda constant was a mistake, but he called it his biggest blunder, actually. But it actually wasn't. The universe was indeed expanding. He used this term to account for the universe being constant, but it was not, in fact, so. And then we have h pi g over c to the fourth, which is the coupling constant on how strongly the energy mass curves space-time. And we have T mu nu, which is that stress energy tensor, which encodes for density, pressure, and energy flux of matter and radiation. Okay. So let's get to the good stuff. This is gravitational lensing. And gravitational lensing is very interesting. It occurs when light from a distant source passes near a massive object. And there's a galaxy, cluster, or black hole that kind of bends that, right? So the mass warps the surrounding space-time, which bends the light path towards the observer, and it magnifies anything behind it at a sweet spot. So it was first predicted by Einstein in 1915, first confirmed by Eddington in the 1990 solar eclipse, and this is when Einstein quite literally became famous overnight. And well, he was famous in before with his golden year of papers, but this is really when he became a celebrity known to the common man. So it was light from a star near a solar limb was observed to be deflected by 1.75 arc seconds, which matched general relativity exactly. Okay. I'm sorry. This is just a little bit more math. so the angle of the deflection angle for general relativity is alpha is equal to 4gm over c squared times b. Alpha is the deflection angle in radians, and g is the Newton's constant, and we have the mass and the speed, and then the correct number. So this has a lot of implications.
So, I just
okay. So this implies that there is a sweet spot for the angle. The deflection angle is kind of like I'm trying to better image this. I could draw it out. So I don't know if you guys can see this too well, but let's assume we have a massive object. Oh, that's terrible. Okay, I'll be the massive object. I'm the massive object. This is you. Let's assume this is some other body. So the angle is, this is emitting light, it's a star, let's say, and it's emitting light curving around me. There's a certain point, like certain angle that will actually be able to curve, a critical angle. If it was too close, the curvature really wouldn't curve to hit the observer. So there needs to be like a sweet spot, and that's really what the angle means. Okay, there are three types of gravitational lensing. There's strong lensing, weak lensing, and micro lensing. Strong lensing is really where you see these amazing images of gravitational lensing. It's when the lens mass is very large, like a galaxy cluster, and it produces the Einstein rings and multiple images, giant arcs. Weak lensing is harder to observe, and you need a lot of galaxies to observe this statistically, and many background sources slightly distort the background mass. Microlensing is very interesting as well. It's a compact object, like a black hole that is transient to the transiently amplifies the background star's brightness, and no spatial resolution is needed to detect a micro. So it could be like an exoplanet or a free-floating black hole. This one's not observed as much as the other two. And this is the strong lensing demonstrated by Abel 2744. It's also called Pandora's cluster. And you could see some, I don't know if you could see it too well, but there's a lot of gravitational lensing here and here. This one is around a galaxy. I have better examples, so we'll be better. Okay. So we'll talk a little bit about weak lensing and cosmic shear. So individual galaxies' shapes are intrinsically random, but lensing introduces a coherent alignment, which is called shear, the patch of the sky. By measuring ellipticity correlates across thousands of galaxies, we can infer the projected mass distribution, including invisible dark matter, because the light actually can curve through the dark matter space, which is very interesting. So it allows us to detect the mass. So the shear signal is very tiny. It's around 1.1 to 5% ellipticity distortion per galaxy. So you need a lot of statistical samples. And there were some surveys that are done, and one that's being done, which is the Euclid and Robin LS, which will billions of force down.
And the color Steve Cosma.
What is
That's good to mute.
Yeah, tell him to mute.
Yeah, of course.
Everyone online, please make sure you've muted yourselves, okay? Thank you.
Thank you. Okay, and microlensing is when a compact object, as we talked about, passes in front of the background star, and it's a very weak lensing that follows a characteristic, I don't know how to pronounce that word, light curve, no image resolution required, and there's an equation for it.
Slow down.
Ignore the equation, it's not that important, I promise. The microlensing is very hard to observe in nature. Okay, but we're going to talk about the largest type of lensing, which includes the Einstein rings, the strong lensing.
He's incapable.
This is the perfect sweet spot. So this is a really, really good example of the Einstein ring. This is the horseshoe Einstein ring. It's considered a near perfect Einstein ring, and the source galaxy is 10 billion light years away. The lens galaxy is around 6 billion light years in distance, which is huge. And the alignment is near perfect because curve is very nearly perfect, very nearly a circle. The magnification factor is around 20 times, making it appear much brighter than it would otherwise. It was discovered in the data set, imaged in 2007. I'm sorry. I lied to you guys, I'm sorry. You wouldn't have listened to me otherwise. Okay. This we already talked about. The angular, well, not really. The angular radius is kind of how much you're going to see about Einstein ring, like how much angle. So for the, we're going the wrong way. For this one, it's nearly 360 degrees, but not quite. So when does a ring form? The perfect Einstein ring, again, requires nearly collinear alignment of the source lens and observer, and the probability is very small, but the universe is very big, so we can see it'll happen a lot. And the lens must be smooth and symmetric, so you can't have a clumpy galaxy. I have an image, I believe, to show this later. So there are multiple types. We have quad, which is a cross, a double, and a full ring. I'm going to show you that. So these are some very nice images. We already saw the horseshoe, which is the first one. The second one, the one to the right, that is an Einstein cross. It's a quad image quasar, and gravitational lens is a nearly spiral galaxy. That was really beautiful. And the next one is a double Einstein ring. It's a little hard to see, but it's very faint around the other one, and that's also an anomaly. SDP.81 ALMA is ring image with unprecedented resolution and radio wavelength. This one, I believe the lensing the lens for this one is hidden in some sort of, you can't really see what is the lens. Like these, they have a clear center. This one, it's an anomaly for that reason. And this is another example of multiple blue arcs, just larger arcs. That can happen because the galaxy is clumpy. So we're going to talk a little about how this relates to dark matter. So what is dark matter? No one really knows, but we could assume how much we have in the universe. We know there's 5% baryonic matter, which is the normal stuff, the stuff we see around us. There's 27% dark matter. Dark matter doesn't emit, absorb, or reflect on the electromagnetic radiation any wavelength. It is detected through gravitational effect, rotational curves, lensing, and large-scale structures like LIGO. And it is not black holes, not antimatter, and it's not ordinary gas clouds. The leading candidates, I don't believe in these, but these are the candidates. WIMPs, which is the weakly interacting massive particles, axions, sterile neutrinos, primordial black holes, and there's also a lot of dark energy. No one knows what that is either, but they're, yeah, physics is hard. So here we go. This is why they believe dark matter was originally, this is why they predicted dark matter was in the universe. So they observed galaxies at their tail end, at the larger radius. We thought there would be, we predicted that there would be a lower velocity because it would like drag behind when it was spinning, because there's no way it would be able to keep up with the rest of the lower radius pieces. We observed that it was kept constant, so there must be some factor keeping it constant instead of letting it trail behind when the galaxy spins. So we attribute this to dark matter. And the Bullet cluster is a fantastic example of this. So when these two galaxies collide, we see that a lagging amount of dark matter, and they're able to, it's led by an electromagnetic drag, but the dark matter halos pass straight through them. And the lensing maps show that the mass concentrated where the dark matter is, not where the gas. So the gas is not bending the light, it's something else, and we believe it's the dark matter. Or they believe, I don't know. And this I know. You could reconstruct mass from lensing, this is the most important for sure. So there's an equation for it. I know. So this critical surface density is basically predicting how good the lensing is, like what kind of conditions we have. If it's equal to 1 of the critical density I was talking about, the perfect angle is the sweet spot. That's where you get the Einstein rings, which are super nice. If the K is less than 1, which is the weak lensing, K is greater than 1, strong lensing. So you use that to reconstruct 3D mass profiles via D projection, which sounds very hard. And I assume they would use a computer simulation for that. And this is the Navarro-Frank-White density profile. This is the equation they use for that, and it kind of characterizes the density from the center, which is very interesting. So they can calculate the mass of this dark matter just from observing how the light bends to it. That's ridiculous. That's amazing. That's so fascinating. So some people believe that dark matter is not just the halos, but there's some vast filamentary cosmic web that connects these galaxies, and they believe they even could form on these filaments, and like the voids are nearly empty of both, such as the Bottas void or something else of the matter. And there's been, as you mentioned, the weak lensing surveys, which have mapped the cosmic web over huge volumes of space. They're still working on those, and it's really interesting to see what the results would be. We talked about the pattern of structural matches, like the cold dark matter constant, which simulates remarkably well on larger scales. And on a smaller scale of kiloparsecs, the tensions remain because the missing satellites and too big to fail problems are still in that. And it's just with the spinning of galaxies that they don't know how the dark matter would completely interact with that. Some believe dark matter is actually just another property of gravity, which maybe could be. So now let's talk about what's being done today. So James Webb Space Telescope is leading a new era in the lensing science. It's providing 10 times better sensitivity than Hubble and infrared transformative for lensing, which is transformative for lensing. The JWST can image lens galaxies at a z greater than 10, which is basically seeing the universe 50 million years old. Crazy. And it also discovered this. If you look over here, this is Arundel. It's a single star at 400 times, 4,000 times magnitude by lensing cluster, and it's the most distant individual star ever observed. Is that one really, really small? And there's a time delay equation. It's not very important, and we have some telescopes that are revolutionizing the field. We have the Euclid Space Telescope, established by the ESA in 2023. It's a wide field survey of 15,000 degrees of sky. It measures weak lensing shapes of the 1.5 billion galaxies, and it's trying to map dark matter distribution. And the other one is the Rubin LSST, and it's a 10-year legacy survey of space and time. It's going to image 37 billion galaxies. Crazy. And trying to make strong lensing discoveries. It's expected to find around 100,000 new strong lensing systems, which is pretty good. Okay. And these are some open questions. They're still very confusing for scientists, like what's dark matter made of, and all these other problems about maybe modified gravity and missing satellites. It's very interesting now. And yeah, this is just a review of what we covered. It's very interesting. Just gravitational lensing is very interesting, and how it relates to dark matter. It's absolutely bizarre how humans have been able to come to this. And I like this quote by Einstein, which is, "The most beautiful thing we can experience is the mysterious." And I'll leave you with that.
Do you have any questions?
Obviously very complex.
Yeah.
But, couple of questions. On the Einstein cross, it's showing four images of the same object.
Yes.
But is it because of the distance it is from the object that's bending this light?
I think it's the distribution of the mass within the lensing galaxy, or whatever that lens would be. I thought I had a picture on here. Can I look up a picture?
Yeah. Can you go back to your screen that has the cross on it?
Oh yeah, of course, yeah.
That was the examples of Einstein rings. Yeah, that one.
I found a better picture on another website that more clearly describes how the lensing would work with different lens masses, and it showed like if it was like a clumpier mass, then it would distribute differently. We would call something like an Einstein ring, or something like just wide arcs instead of like a clean double ring, or maybe a single ring.
So that's a galaxy in the middle of the
Yes, that's a galaxy in the middle.
So on the Einstein ring, how do they actually predict the angle that light is hitting and the distance that object is from the actual galaxy?
I don't have the distance equation. I do have the angle. Is this one? Yeah. I think there's another one for distance, and they use that for they use that for this equation, the Einstein ring angular radius.
Yeah. One other question.
Yeah.
If I looked at the Einstein cross,
Yes.
and I could separate each image, would they show the same spectrum?
I'm not sure. It's a good question because it is being bent. So maybe. I don't think it would. I feel like it'd be different because different parts of the Einstein ring. That's a good question.
Why isn't there a ring instead of a cross?
Like, why is it a cross instead of a ring? I assume it's to do with the lensing galaxy that's in the center of it, or whatever lensing mass is there. It's like maybe clumpier in some way, or it has a weirder distribution than something like a black hole, which would be a very uniform distribution, or like a spiral galaxy, which would be a very nice distribution compared to something like
Good job.
I tried.
I don't think you can see.
Okay, yeah. My question is, like, when the gravitational lensing happens, does it redshift the photon?
Yes, that question. I don't know because I don't know if we changed the frequency or redshift or I don't know. Maybe physicists don't even know. Maybe you'll be the first to figure that out. That'd be so cool. For a whole PhD on that.
Matthew, if you could repeat his question so people online can
yes.
hear.
He asked if the gravitational lensing would redshift the photons, which is a really good question. I'm not too sure about that. Maybe.
Well,
Well, if it increases the magnification,
Should.
then it's either blue shifted or red shifted.
Yeah, there's no way it stays the same, right?
I mean, I'm pretty sure it's redshifted because it's some sort of like energy required to escape the gravitational field.
Hmm.
So it's in that process it loses energy.
That'd be very interesting. Yeah. I should have included something on that. It's a good question.
I had a question, you go forward a couple of screens. There was something about, oh gosh, was it Euclid or something that they mapped something. I wanted to know what telescopes or whatever they used to do some mapping. Keep going.
That's it.
Was this one?
No.
Euclid Space Telescope? Like which telescopes they used for?
Yeah,
Honestly, I don't know.
okay.
I
I think I've lost my question.
That's fine. I have a lot of questions too about this stuff because it's just it's really on the cusp of technology and what we know so far. It's just very, very interesting, and it's a very new field, so that's very cool.
There's some people online.
Oh, online people, do you have questions?
Go on muted, right?
Oh, better be.
If you have a question, please unmute yourself.
Yeah, I'll mute yourself if you have a question.
Nice equations, Matt.
Thank you. I took them from someone smarter than me.
You shouldn't have said that. I mean.
Yeah, my original work actually. Yeah, I don't know who Einstein guy is. Supposedly.
Matt, have you looked into the potential of using our sun as a gravitational lens for observing surface details on exoplanets within our galaxy?
That sounds amazing. I believe they've used the sun for gravitational lensing before. I don't think they've done it for exoplanets. That'd be very interesting. I don't know how how much detail they would get out of it, but it sounds like very, very interesting. It's a good question. Thank you guys for bearing with me.